I'm delighted to be here, of course, and I thank John McKay, and pleased to get to know him, and Pat, and Annie. And I've been inspired by the broadness of Pat's introduction yesterday, and by what I've heard here, from wonderful molecular chemistry through to 400 million years worth of adaptive evolution. That's quite a spectrum you've arranged, John. And I've been inspired by John McKay's laid-back flexibility. That flexibility included moving me from first speaker to last speaker, which, and those of you who are observant will have noticed that the title is completely changed, and I can tell you that most of the content has as well. So I thought that what I would do is tell you about some extraordinary innovation that went on in Australia during the 8 years of very severe drought that we had in the noughties, as we call them. And at the risk of being a little parochial, I think you would nevertheless be interested in the sort of things that we have been doing at that time, because the farmers are desperate. The mining boom in Australia has brought the Australian dollar to parity with the US, which means they don't get paid much as they used to, when it used to be something like a half. So things are tough for them. They can, of course, buy expensive toys more cheaply from America, like John Deere tractors. So just to go over the background again, which Pat went over, the rate of genetic gain in dryland crops is falling, irrigation water is becoming scarcer, more grain is going to be needed globally from semi-arid environments. Selecting for yield is just about impossible in highly variable environments where you've got a factor 5 range in seasonal rainfall easily. And I think organisationally we've got inadequate connections between agronomy, pre-breeding and breeding, with the possible exception of Pioneer, where we were told that everything was in pretty good shape, and I believe it is, in Mark's area. So we throw around the term drought tolerance, which Pat defined very broadly to include just about everything you can think of in relation to crop production in water-limited environments. So I think it's not, I've got here or, but I don't think it is either or. It's just complementary ways of looking at the same issues. But what attracts me to productivity is that it has units, and I like things with units because you can tell whether you're making any progress or not. So measured as kilograms of grain per hectare per millimetre of water supply, or if you're a farmer, dollars per hectare per millimetre of water supply, because you're not going for the ultimate water efficient yield, you're going for your best gross margins to keep the bank manager happy. So sources of agricultural innovation, bottom up, and we've heard a lot about gene discovery, which is the ultimate bottom up, and its influences on possible performance in the field. Top down, starting from the field and going down, and we have a lot of terms like extension, technology transfer, delivering outcomes, which give the impression that the process is wholly linear from the lab to the field, and we all know these days that it isn't. So here is a common successful pattern, of which there are many examples, in which acute observations in the field are explored and drilled down layer by layer until you get to some sort of understanding of what might be causing you a problem, and then you try to come back up again. And one of the most beautiful examples of that was described in the first talk by or second talk by John Passioura, starting with the observations of what happens to droughted corn and drilling down to eventually senescence genes as well as the carbohydrate metabolism genes. And that puts you in a tremendously good position to start coming back up again in ways that you might decrease the sensitivity of the plants to water stress at about the time that John was talking about. Now, the history of domestication of crop plants is the removal of various forms of conservatism, like shattering ears and height. And my feeling is that there is still too much conservatism in the area of floral fertility, and also in the area of senescence during grain filling, where one hot day can send the plant scurrying for home when there may have been 2 more weeks left of grain filling available to it. So embedded in this fairly broad picture here, I should emphasize that the boxes that I have filled with words there are what goes on, I believe, during conversations between field scientists and farmers. Farmers are, the best farmers are tremendous observers. They see emerging problems or current problems. They let the field scientists know about it, who respond to those. And on the other side of the coin, going from the field scientists to the farmers, there are new options, new solutions, new opportunities, and new concepts which will stimulate the farmers. Now, this area here covers quite a bit of stuff, and this is a bit more detail of the various levels of organization into which plant biologists put the broad sweep of their subject matter so that they can make sense of it. What's interesting about this broad sweep is that you need often different language at different levels, and you can get some terrible confusions when you get, say, a molecular biologist talking to a farmer, or even a plant physiologist sometimes. Confusions both ways. So you'll have often seen this, this linear display of levels of organization, but it seems to me that it's more meaningful to turn it into a closed loop, because unless the loop is closed, none of the structures and processes, etc. within it would exist. That's what enables evolution. And for our game, it's selection at the community crop level that leads to genes getting into the next generation of crop plants. Gene is a very simple summary of it, but call it gene frequency if you like. But there's been a fair amount of work since the molecular biological revolution of trying to go from here to here in one step, whereas what I described earlier for John's work is starting here, going through just about all of these layers down to here, and in a very good position now to come all the way back again. And unless you can scale up well, you can fall foul of many of these stages. For example, at one stage there was a tremendous amount of work going on with Arabidopsis and salinity, in which Arabidopsis was put in something equivalent to seawater, and the cells plasmolized, that is, the cell membrane was ripped off the cell wall as water was sucked out of it, and this leads to enormously good gene expression, but it doesn't mean very much. So talking about single gene transformations, what works? So I've tried to summarize what works. Now, the big ones, Bt and herbicide resistance, beautifully simple, seemingly no metabolic disruption of the plant itself, no demands on photosynthate, and they're working on an outside influence, not on what's happening inside, and they're wonderful. Not far behind, but nowhere near economically in the same class yet, is genetics of grain quality, where single genes can have a substantial effect, especially in the oil seeds. And the plant can't get back at you because it's end product metabolism, storage in the seed, although it can get back at you in some circumstances, where some colleagues of mine were trying to convert linoleic acid into an epoxy form for industrial purposes, and were delighted with the high yield that they got, except that the seeds wouldn't germinate anymore. And when they looked into it further, where they got the original gene from was, I think it was in euphorbia of some sort, which was accompanied by a suite of other enzymes that were required for the germination. Disease resistance is starting to look exciting, I think, especially in the rust area, where we know that there are single genes that can confer resistance to various races of rust, but they tend to break down. But the understanding of what's going on there is becoming really good. But something like abiotic stress, we've heard interesting stuff on single gene possibilities in drought tolerance, but yield is the culmination of the whole season. Drought can occur at any time. If you're playing around with the metabolism of the plant, all sorts of things can go wrong, and there are many feedbacks and interactions. So in that area, if you look up, if you search for plant breeding, drought tolerance or drought resistance, and transformation, you will be delivered 1,000 papers, roughly. So to my knowledge, only half a dozen of those have ever made it to the field, and also, to my knowledge, none of the published work on the field research has proved convincing that there is an improvement. So is drought tolerance a genetic goal? For a breeder it is, yes. And for an agronomist, no, because the agronomist is concerned with all stages of the crop's life, not with, well, I don't mean to downgrade breeders in any way, but just the final yield. And what is the common ground? Well, this is the best example I've come across of the breeder's view of drought tolerance in wheat, where plotted against the yield of what was then the current best variety, a new variety was pretty well indistinguishable from it. In the range of yields, this is over about 100 experiments, from 1 to 4 tonnes, but improved dramatically for yields less than, say, 2/3 of a tonne. And that looks great. But if you're looking at a yield of half a tonne, then a 20% increase in yield is 100 kilograms per hectare, which is not a very riveting improvement. And anything less than that, and a farmer is thinking of putting the stock in. Because when you've got a drought like that, either putting the stock in or harvesting it for hay can be valuable. So the agronomist's view, to repeat the productivity one, is that we have got a series of problems in using water, capturing water and using it to good effect. And that is broadly summarized by this chart here. in which you've got your water supply and you've, no point in using this, you can see it. You've got your soil water at sowing, you've got the precipitation during the season, you've got a range of losses, net runoff, which is usually small except in where you get torrential rainfall, deep drainage, which can be very important, and very large losses by evaporation directly from the soil, at least in a winter growing environment that I'm used to. You've also got water that isn't extracted by the crop but could be if you are getting everything right. And that leaves you the transpired water, which through this operator of transpiration efficiency and all of the biochemistry of allocation and so on, is turned into biomass, above ground biomass. No one really knows what the below ground biomass is. And then harvest index, getting it into the grain. And for wheat crops, here are some numbers that are essentially the ecophysiological limits at the moment. You can get about 55 kilograms per hectare millimetre of dry matter, and in a drought-prone environment, getting a harvest index above 0.4, especially if you're maturing into warming conditions, gives you a limit of about 22 kilograms per hectare millimetre. Now, this graph, which was prepared by Victor Sadras and John Angus a few years ago, illustrates the clarity of the frontier between experimental results and the rest of the world. And every few weeks you will see in the newspapers that there is a gene for drought resistance. And if you spend a lot of time talking to people at parties and so on who ask you what you do, and they tell you that, and you tell them and they say, oh, well, we're going to solve the problems of lack of water with drought resistance. If you're thinking of getting up into this space, then we might be a century or two away, I think, from getting there. Now, what's interesting about this graph is the tremendous spread of points in here. I think a great deal of that spread is, especially down this end, is due to catastrophes at the time of anthesis or building up to anthesis. A stinking hot day during anthesis and you're gone. A lot of it is also due to poor management in which you don't have a substantially good production of biomass, and you haven't built up enough biomass by the time of flowering. You haven't built up a sufficient factory which you can then use to make the product of grain from then on. Now, we thought for a while that if you talk to a farmer who's got a point down here who complains that it isn't up here, a better way to look at it is to look at it this way, that the intrinsic photosynthetic water use efficiency, dry matter per unit of produced per unit of water, is pretty much the same whether your crop is starved of nitrogen or has got heaps. And the reason for this point being low is not that the slope has changed, but there has been a trebling, in this example, of the amount of water lost by direct evaporation from the soil. That water has just gone back to the sky and has had very little productive effect. So here is a list of manageable components of the water economy of crops, which you can map onto the previous skeleton framework that I showed you. One of the things that faced the Australian croppers during the 8 years of drought was not only that there was rather less water, but that the distribution of water had changed so that there wasn't much water during the fall, during the planting period, and the water had, the rainfall was now falling in the summer. So the farmers were soon onto that, and they were assiduous in controlling weeds. There's nothing much you can do about rainfall that is evaporating from the surface of wet soil. But that falls off with the square root of time. It goes fast to start off with and then tapers off until the top 20 centimetres might be dry, but underneath is wet. But if the roots of weeds get down there, the whole lot can go. And it doesn't take much of a weed to do that, because if you think of 100 days of summer, 1 millimetre a day of transpiration from weeds, and the lot's gone. So exploring that a bit more, the farmers were desperate to plant at the time they thought was right, but there were no planting rains, but they knew that they had 2 tons of equivalent of water in the soil. So they wanted to know whether it would be feasible and not too risky to sow dry. A few of them tried, but many were nervous, and several of us were asked to go around the countryside. We mobilised what information there was on the behaviour of germinating wheat, and showed that as long as there weren't about 40-degree days of germination before the soil dried out again, they worried about a false start. Planting rains, then nothing else coming on. Then the seeds would survive. And this gave them the courage to sow dry, and very large acreages were sowed dry with very good effect, because an agronomic consequence of waiting for planting rains is that if you only get a week's planting rain, that's the time that you've got to sow, and it might take you 3 or 4 weeks to sow the whole farm. So you've only sowed a quarter of the farm, whereas you can do things carefully, so on, when it's dry. They could only do it when it's dry if they have been using conservation agriculture, so that the sowing equipment can go through the soft soil, and only if they've got weeds totally under control, so that the germinating plants won't need to deal with them. So that was one form of innovation which came from the farmers, mobilised scientific knowledge, and gave them the courage to do what they wanted to. So all of these things are fairly obvious when you settle them down like that. But that framework applies not only to management, but also to breeding targets. And this is the same list highlighted to show you targets for pre-breeding. And many of those targets are now being pursued by pre-breeders or have been solved. Now, Richard Richards was here a couple of years ago, and he may well have showed you this list of traits that he's using in his breeding program, for those of you who were here then. And we've got a range of traits that we believe are likely to help plants capture more water, use it more effectively in producing biomass, and then harvest index. Seeding establishment I've just mentioned, But if you're going to sow dry, you often want to sow deeply to get to the water that you know is down there. And if you're using semi-dwarf wheats, you can't sow more deeply than about 40 millimetres, 40 or 50 millimetres. So Richard has had a substantial program going looking for alternative dwarfing genes which will give you a short stem but at the same time a long coleoptile. And he's got that just about to the point of release now. Vigorous shoots capture water that would otherwise be used by direct evaporation from the soil, and root vigor and root length in capturing water in the soil is fairly obvious. Transpiration efficiency has been effective, and genetic variation in the amount of carbohydrates stored in the stem before anthesis and then mobilized, or even after anthesis, briefly, and then mobilized into the grain. There is genetic variation in that, and so on. And I'll just show you a few of these. This is what happens to standard semi-dwarf wheat that is sown at 6 inches, and this is the long coleoptile variant of that there, which has much better emergence, as you can see. And that shows you the difference in the length of the coleoptiles. This shows you the difference in vigor that the breeders have managed to get from a standard variety, Jans, to the varieties that are about as vigorous as barley coming out of the ground. Increased root vigor, there's substantial variation, genetic variation there that is being used. And grain number after drought at meiosis looks, which is drought at meiosis can be very damaging to fertility. We're comparing here a standard variety that's commonly used with a synthetic hexaploid, and that looks promising, and they're running with that now, although it's going to be a very slow process. I mentioned to Mark earlier that there's a very nice review by Antonio Hull from Buenos Aires and Richard Richards coming out in Field Crops Research, which looks at the time taken from having a good idea to getting a variety that might be useful in the field. And it's essentially a minimum of 20 years. And they also point out that even something as seemingly simple as getting RHT1 into bread wheat took 8 years of shuttle breeding by Norman Borlaug. That's 16 generations to get it right. And Mark's also into the shuttle breeding business. He gets 2 generations a year too, which halves the amount of time. So something like this that we're showing here, I think, would take a fair while to come. So this is the current situation of progress in making markers or identifying markers or genetic regions, whether genes are identified, and the cultivars released. There have been 5 cultivars based on carbon isotope discrimination leading to improved transpiration efficiency. Several include glaucousness, which reflects heat from the leaf and improves water use efficiency. And the seedling establishment one with the long coleoptiles are close to being released too. But that's been a long haul because getting RHT1 in was difficult. If you're trying to get an alternative dwarfing gene in, they were hampered for a while until they had cloned RHT1 and could select against it in the early stages of their crosses. So these are the agronomic trends that I can see, and I've heard some pleasing confirmation of those observations during the last 2 days, that we're moving into an era, I think, in which we're going to tailor genotypes and management to complement each other. And going back to that issue of sowing early and dry, and it can be quite early, that was also made possible by the breeders having enlarged their focus on maturity. And while you want the plants to flower at the right time, there's a much greater range in maturity classes that you can sow at different times and get them to flower at the right time. So long maturity, early sown plants were used with some late summer rains to sow and get your crop going. And tactical responses as the season unfolds is the essence of what enabled the farmers to get reasonable yields in most years, 6 of the 8 years of drought, which any one of which 20 years ago would have wiped out the whole industry for that year. And there's a great deal of interest in spatial analysis and management. So, but also during this period, there was a range of novel options that were invented. And one was the adoption of dual-purpose crops that a visionary breeder had started to produce 20 years ago, which you could graze during the winter time, and which had a small vernalization requirement, which meant that the growing tips were beyond the mouths of the sheep. And the surprising thing about this type of management was that it often led to higher yields than if you didn't graze at all. And you can see that's a 25% increase in yield there, due to the fact that the wheat was grazed to the ground over a period of about a month. And we assume, although it hasn't yet been properly shown, that that's due to the saving of water during the vegetative period for use during flowering and grain filling. Well, if we're going to have a greater emphasis in pre-breeding, and with the burgeoning industry of phenomics, presumably we are, then we have to make the most of phenotyping in controlled environments. And I'm not sure if we are doing so yet, because the high throughput phenotyping industry, if I can call it that, is at a stage of developing tools which will enable them to measure various things rapidly on large populations. But I find it a little sad and discouraging that they're treating this as a problem in series rather than in parallel. And my belief is that they should have pre-breeders on the spot, that is, people who can incorporate interesting traits and the genes representing them into advanced germplasm right from the start. And that, I think, will save a great deal of lost time on building very expensive machinery for making trivial measurements. Don't say that to any of my friends in phenomics. And that's our second point there. Now, the other thing that I have been puzzling over, and partly inspired by the work of Mark Cooper and Graham Hammer, is that a lot of the traits that we've become interested in deal with specific times of development during the life of the crop. So if you're interested in seedling establishment and you've got good planting conditions, then it's irrelevant. And one hopes that it doesn't also have negative trade-offs anywhere else. Similarly with having vigorous early growth, which enables you to get biomass for free, in effect, because you're using water that would otherwise disappear anyway. That is very prone to a trade-off problem, because it will certainly be using not only the water that would have otherwise evaporated, but more water in the soil, and you run into the problem of not having enough water for later on. So the question is, if you've got a lot of what I call 20% traits, they might be valuable in 1 year and 5, and you've got some nice germplasm in which you've got positive negative and positive expression and no expression of the particular trait, and it does very well in the target environment, and you then persuade commercial breeders to take it on, is it going to persist in their breeding programs when they're obsessed, and rightly so, with disease resistance, height, grain quality, and yield if they can get it? And if they haven't got those, any variety they produce won't be accepted. So they don't have the time to look at fancy selection, at least in our environment. So how do you go about bringing these together, and in what circumstances? So a good climatic analysis coupled with modelling of the sort that Mark showed earlier can tell you, for a target environment, how much value you should put on these. But then we could have been talking about this in the year 2001, before the drought started, and we're blown out of the water so far as the target environment is concerned. And for example, long coleoptiles are important just about in every year, rather than 20% of years. So I'm not sure how we go about getting 20% traits persisting in breeding populations with commercial breeders who are under the hammer, unless you've got a very big outfit like Monsanto or Pioneer. I believe it's extremely important to connect breeding, pre-breeding and agronomy. The national variety trials, which in wheat Australia runs every year, all of the varieties are planted at the same time at any given site. You don't have the opportunity to explore agronomic experiments coupled with varieties of, say, different maturity class in those circumstances. And I mentioned earlier that we have been creating a greater range of genotypes for different agronomic environments. So we set about developing field phenotyping facilities across the country for demonstrating the breeding value of specific traits, which only accept material which has the traits incorporated into well-adapted genetic backgrounds and tested with realistic crop management, including the ability to sow at different times. And it's essential to involve the breeders, pre-breeders and agronomists from the beginning. And that's how that's set up. And I want to finish with a tribute to this fellow, Wilhelm Johansen, whose paper in the American Naturalist had its centenary last year, and it was the first introduction into English of the words genotype and phenotype. And he invented those words because he was having a row with Francis Galton and Carl Pearson, who noted that there were complex characters with, say, roughly normal distributions, and they had assumed that you could select from those normal distributions to create different genotypes. What Johansen managed to do was show a normal distribution, I think, of the size of beans in identical genotypes, and that blew them out of the water and left us with the terms genotypes and phenotypes. So here's to Wilhelm Johansen.